So hi guys, today we have another problem that is minimum cost to fill given weight in a bag. I'm not going into the detail of the question. Basically, this is a modification of unbounded knapsack problem. Okay, so if you know unbounded knapsack problem, then try yourself. Do not watch this video right now. If you cannot, then come to this video. They are making slightly difference from that question. Okay, so if you don't know what is unbounded knapsack problem, go and study yourself and then come to this video or try to solve this one. So let us see what the question states. Basically, you are given the cost. Obviously, in that question also we had the cost, but you cannot see the weight array also. What is the weight array? Basically for this position, the weight is 1. For this position, weight is 2, and so on. Basically, the one based indexing. Okay, and the capacity of the bag is given, that is 5. So now this problem is simple. Just you have to implement the unbounded knapsack problem and slightly modify it. So let us discuss for the modification. What can we do? Basically, I'm not going into detail again. Just I'm telling you the take non-take part, and that the what modification that we need here. That is basically for non-take. For non-take, it will be basically let us say solve function. I'll not consider the current element, so I'm reducing the index. Obviously, index is started from the last one, so it will be easy, and weight will be as it is. And for take part, take will be index will be as it is. Why? Because maybe in future I consider that element again, because the supply of the element is infinite, and weight will be weight minus I plus 1. Why I plus 1? Because of I have already told you that the weight, that is basically one based indexing. So this will work, and we need to just implement this function. And what is base case? Basically, when the I element is pointing to the zeroth element, and then we have to make the base case. And what is the base case? Suppose you are now positioning on the pointing on the first index, and you have weight, that is 3, suppose, and we know that for the first index what is the weight, that is 1. So how many instance that I can take from here? That is obviously 3. Okay, so we have to return uh, weight, that is current weight, into say, let us say, what is the name of the cost? Okay, it is cost. So let us say C of 0. We have to return this one, and also we have to add another value, that is current cost of I, because we are considering that value. So then we have to return the minimum of those, because we already know in the unbounded knapsack we always have to keep the cost minimum, and that will be minimum of not non-take and take. Just we have to return this value, and then we can apply DP and memoization to optimize this problem. And let us see the dry run. I'm not writing the whole diagram because I'm using mouse. Okay, it will be taking a lot of time. So here initially I do not have anything in my pocket. So what is the available weight that I can consider? That is 5. Okay, so this is our example, and the cost and the capacity is 5. So initially the capacity will be 5. So now I am taking this 50. So the current cost, that is 50, and the remaining weight, that is 1. So again I can take 50 also, but you can clearly see that if I take the 50 again, then the capacity will be going to be negative. So I cannot consider this one. So I have to return uh, maximum value, or you can say int max. Okay. So now let us consider for the another case when I'm not considering that element. So now I'm not considering that element. So moving this part, the cost will be same. And now I'm taking this 4. Okay. So the weight, that is 54. But you can see that again the capacity, that is going to negative. So we cannot take this path also. So returning max value. So again, I'm not considering that part. So now this is the time to check for the 10. Okay. So I'm taking 10, and what is the weight of the 10? That is 2. So 1 minus 2, that will be minus 1, and this is negative, right? So we cannot take this part also. So return max value. Okay. Now you can see that if I consider the last value, that is 20, and the weight, that is 1, so the weight is now 0. So this is the positive base case that we can reach. And what is the cost? That is 70. So now you can return 70 or this part, because I have made the algorithm like this. When I'm going deeper, the cost will be added simultaneously. Okay. So when we are returning the value, basically this value will be added into this cost. So basically, uh, you can return the base case value, or you can have a calculation from the beginning. That is your choice. So now we can return this positive value, and one can be this can be our answer. But let us check for the another path. Maybe that path will make the least amount of cost. So now check for this path. So I'm not considering 50. We will start from 4. So I'm considering 4. And what is the cost of the weight of the 4? That is 3. So 5 minus 3, that will be 2. And then I can again take 4, and you can clearly see that it will make the negative value. So this is a negative base case. So to return max, and here you can see that if I consider 10, then what is the cost of what is the weight of 10? That is 2. So 2 minus 2 will be 0, and I can add 10 into our answer, into our cost. So that will be 15, and this is the final answer. Okay, this is the minimum one, and you have to return this value. So you can generate all the other paths in, but you cannot find the um, minimum one. So this is the minimum one. I'm not drawing another parts also. It will be huge. So this is how you can solve this question. And this is the recursion tree that we have here. And also the duplicate paths that we will store into the DP vector. So yeah, this is how we can solve this question. And obviously, first of all, if you do not know what is unbounded knapsack, go and study. Otherwise, you cannot understand anything that I have said here. So let us try to code it. So we need to make the vector or DP. That will be vector vector int DP. DP will be what? That is the size of n, and vector int, it will be the size of w plus 1 and minus 1. Why w plus 1? Because I'm considering from weight to until to 0. When the weight is 0, I will go and check for that. So 0 to that current weight, that will cost me weight plus 1 size, right? So I'm taking weight plus 1 here. So now let us make the solve function. We will store the answer into another variable that will trace. Will be solve. We have to pass n minus 1 weight also, and dp and cost. Okay. So return if the race is equal to int max, then we can return minus 1, else we can return race. I will discuss later why I'm taking int max here. So Now in solve it will be uh, int index, sorry, and then int weight, then vector, sorry, int dp, obviously passed by reference, and vector int cost. Okay, so I'm not writing the base case right now. Let us clear all the things, that is take or non-take. Int non-take, it will be simple, just idx will be idx will be idx minus 1, weight will be as it is, and dp and cost. Okay, and int take, initially the value of the take will be int max, and then we have another condition that we have to satisfy, that is basically mm, current position, the cost of idx, it should not be minus 1. Why should not be minus 1? Basically, in the question, they tell you that if in some position you can see the cost is minus 1, then you can understand that the position, that the element that is not available right now. So I cannot take that element. Okay, so moving backward, and there is another condition, that is the value of the current weight, that always should be greater than equal to IDX plus 1. Why IDX plus 1? Because we have to check if I can afford that much weight in our bag or not. If that is going to be negative, then we cannot take that. I've already told you in that diagram. Okay. So in the next part, uh, let us calculate the take part. That is, take is equal to the current weight, sorry, current cost, that will be IDX plus the function that is solve, it will be idx as it is, weight will be reduced, that will be idx plus 1, and dp will be same, cost will be same. Okay, so then we have to return it into the dp, and that is dp of I, not I, idx, and weight will be minimum of take and non-take. And let us write the base case. So what can be the base case? If IDS is equal to 0, then we have to stop and check for one condition that I have already told you. If I'm currently right now, and suppose our weight is 3, then I can clearly multiply 20 into 3. Why? Because in the starting position, the weight of the instance is always 1. So you can initially, you can easily calculate the weight, that will be, sorry, the cost, that will be uh, cost of 0 into what, that is remaining weight. And then we have another condition, that is we have to check if the current position is already stored into our dp or not. That is idx and weight. If it is stored into our dp, then we can return simply that value of that position. Okay, we do not need to calculate the path again, the simple dp concept, the memoization. So let us try to run the code. Hopefully everything is correct. Okay, so it is matching. Let us try to submit the code. It's working fine. Okay, so talking about time complexity, that is obviously n into weight plus 1, or you can say weight, and the space complexity will be same, not properly n into w. It will be nearly about that much, or you can say polynomial, and weight is sorry, and space is obviously n into weight. So yeah, this is how you can solve this question, a general standard question of unbounded knapsack problem. So hopefully the concept is clear to you, and Thank you. See you in the next video. Bye.